Perovskite solar cells, materials, device architectures, fabrication, and optimization strategies. Perovskite solar cells, PSCs, have emerged as a transformative photovoltaic technology due to their rapid efficiency improvements, low-cost processing, and versatile material properties. This video presents a comprehensive overview of PSCs, encompassing materials chemistry, device architectures, electrode engineering, fabrication methodologies, and optimization strategies. Particular emphasis is placed on scalable manufacturing, interfacial engineering, stability enhancement, and environmentally benign material design. Recent advances demonstrate that through integrated materials and process optimization, PSCs can achieve high efficiency, long-term stability, and compatibility with industrial-scale production. The increasing global demand for sustainable energy has intensified interest in next-generation photovoltaic technologies. PSCs have attracted considerable attention due to their remarkable power conversion efficiencies, PCEs, which have risen from below 4% to over 25% within a decade. Their unique combination of tunable band gaps, high absorption coefficients, and long carrier diffusion lengths makes them highly competitive with established photovoltaic technologies. Perovskites adopt the general formula ABX3, where A is a monovalent cation, for example, methylammonium, formamidinium, or cesium, B is a divalent metal, commonly lead or tin, and X is a halide. Their structural and compositional flexibility enables precise tuning of optoelectronic properties, facilitating diverse device configurations and applications. Device architecture and working principle. PSCs typically consist of a transparent conductive electrode, an electron transport layer, ETL, a perovskite absorber, a hole transport layer, HTL, and a back electrode. Upon illumination, photogenerated charge carriers are separated and transported through selective charge transport layers, producing electrical power. Two dominant architectures are employed: mesoporous and planar structures. Planar devices, NIP and PIN, are particularly advantageous for low-temperature processing and scalable fabrication. Perovskite materials and charge transport layers. The performance of PSCs is intrinsically linked to the properties of the perovskite absorber and charge transport layers. Band gap engineering via compositional tuning, for example, halide mixing or cation substitution, enables optimization of light absorption and device efficiency. For example, methylammonium lead iodide remains a benchmark material with a band gap of approximately 1.55 electron volts. Charge transport materials must exhibit appropriate energy level alignment and high carrier mobility. Organic HTLs, such as spirometid, PTAA, inorganic HTLs, for example, nickel oxides, and carbon-based materials are widely explored. Similarly, ETLs include metal oxides, titanium dioxide, tin, oxide, and organic semiconductors such as fullerene derivatives. Electrode materials and interface engineering. Transparent electrodes. Transparent conductive oxides, TCOs, particularly indium tin oxide, ETO, and fluorine-doped tin oxide, FTO, are commonly used as front electrodes due to their balance of transparency and conductivity. ETO offers smoother surfaces and higher transparency, making it suitable for low-temperature processed planar devices, whereas FTO is preferred for mesoporous architectures due to its thermal robustness. To address cost and mechanical limitations, alternative transparent electrodes such as silver nanowires, graphene composites, cadmium tin oxide, and biomass-derived conductors have been developed. For instance, Ag nanowire graphene hybrid electrodes have demonstrated PCEs exceeding 15% with improved thermal and environmental stability. Flexible bio-derived electrodes have also enabled mechanically robust PSCs with high bendability. Metal back electrodes. Noble metals such as gold and silver are widely used due to their excellent conductivity and favorable work functions. Gold provides optimal efficiency and stability, while silver offers a lower-cost alternative, particularly in inverted device structures. To reduce cost and improve stability, alternative metals, including aluminum, copper, nickel, molybdenum, and tungsten, have been investigated. For example, copper electrodes exhibit good stability with minimal diffusion into perovskite layers, while aluminum electrodes enable efficient inverted PSCs with competitive PCEs exceeding 17%. Alloy electrodes, for example, silver-aluminum electrode, further enhance thermal stability and interfacial properties. Carbon electrodes. Carbon-based electrodes, including graphite, graphene, and carbon nanotubes, offer a low-cost and chemically stable alternative. Notably, whole transport layer-free carbon PSCs, CPSCs, demonstrate exceptional long-term stability due to inherent moisture resistance. Large-area printable carbon-based modules have achieved stable efficiencies over extended operational periods, highlighting their industrial potential. Fabrication techniques. Solution-based methods. Solution processing remains the most widely used fabrication approach due to its simplicity and cost-effectiveness. Spin coating is the dominant laboratory-scale method, enabling high-quality films and efficiencies exceeding 22%, although it suffers from material wastage and poor scalability. Doctor blading and slot die coating offer scalable alternatives with high material utilization and compatibility with roll-to-roll manufacturing. For example, blade-coated PSCs have achieved efficiencies approaching 20% through compositional engineering and crystallization control. Spray coating and inkjet printing provide non-contact deposition techniques suitable for large area and patterned devices. These methods enable precise control over film morphology and thickness, with demonstrated efficiencies above 18% in optimized systems. Screen printing is particularly attractive for low-cost, large-area module fabrication, especially for carbon-based PSCs. Vapor-based techniques. Vapor deposition methods, including physical vapor deposition, PVD, and chemical vapor deposition, CVD, enable the formation of highly uniform and dense perovskite films with controlled thickness. These techniques are particularly advantageous for multi-layer device fabrication and large-area uniformity. Hybrid vapor deposition combines solution and vapor processes to improve film quality and reduce defects. Although vapor-based techniques require vacuum systems, they offer superior reproducibility and scalability for industrial applications. Emerging techniques. Additional fabrication approaches include sol gel processing, electrode deposition, and laser-assisted patterning. The sol gel method allows precise control over film morphology and defect density, while electrode deposition enables uniform coating on complex geometries. Laser ablation has been successfully employed for module patterning and interconnection, improving cell-to-module efficiency. Stability enhancement and optimization strategies. Material and interface engineering. Enhancing PSC stability requires controlling perovskite composition, morphology, and interfaces. Additive engineering and defect passivation reduce recombination losses and improve environmental resistance. Interface engineering, including the introduction of interlayers and surface treatments, enhances charge extraction and suppresses degradation. Encapsulation techniques. Encapsulation is critical for protecting PSCs from environmental degradation. Glass encapsulation with edge sealing has demonstrated long-term durability under high humidity and thermal cycling. Polymer-based encapsulation, including fluorinated coatings, further improves moisture resistance and operational stability. Environmental and operational stability. PSCs are highly sensitive to humidity, temperature, and light exposure. Moisture can induce perovskite decomposition, while thermal stress and photodegradation accelerate device failure. Strategies to mitigate these effects include hydrophobic coatings, compositional tuning, and optimized device architectures. Scalability, toxicity, and emerging applications. Scalable fabrication remains a key challenge, with techniques such as slot die coating and roll-to-roll processing offering promising solutions. Toxicity concerns associated with lead have driven research into tin-based and other lead-free perovskites, although stability and efficiency remain limiting factors. Emerging applications include tandem solar cells, flexible electronics, and optoelectronic devices such as light-emitting diodes. For example, all perovskite tandem devices combining wide and narrow bandgap absorbers have demonstrated efficiencies exceeding 28%, illustrating the potential of compositional and structural engineering. In conclusion, perovskite solar cells represent a rapidly evolving photovoltaic technology with exceptional potential for high efficiency and low-cost energy generation. Advances in electrode materials, fabrication techniques, and stability engineering have significantly improved device performance and durability. Nevertheless, challenges related to long-term stability, environmental impact, and large-scale manufacturing must be addressed. Continued progress in materials design, interface engineering, and scalable processing will be essential to enable the commercialization of PSCs and their integration into the global energy landscape.